go on and talk about half of what I wanted to say today, because with the depleted strength today, or do we just call it a day and go in for Thursday? Maybe we'll just make a start today. Okay? Is that okay?
The other three haven't seen our messages. Like me and Arun put up some messages. The other three haven't seen them. So
Yeah, I understand.
we don't know when they'll see the messages.
Okay, so let me do one thing. Let's just set up one topic for today. The recording will be there, so they will be able to follow it up from the recording. We will need it for the next day when we actually will do the proper molecular vibration stuff. Okay? But there is one piece of the basic theory that we have left out till now, and it is a bit important. The proof is not that important, perhaps. It's more important that you know how to use it. So we will use it on Thursday. But today I'm going to just indicate how the proof goes. Okay? So that's what we are going to do today. So it will be a truncated kind of class that way. So let's just make it beginning. What we are going to talk about is what is called projection operators, or basically, this is something which you all know of from quantum mechanics. But in group theory, there's a specific meaning to this. The basic
So
idea.
did
Yeah.
you start presenting? I can't see the screen.
Yeah, I started recording and forgot to present. Thanks for this. It seems the vacation has also put me out of touch a bit. And now I have started presenting. I hope you can see this now.
Yes.
Okay. So we are going to talk about projection operators in group theory. And we will start, well, where else? With this basic rule, which is at the heart of everything in group representation theory. This is, of course, mod G by d alpha, delta alpha beta, delta I j, delta I prime j prime. This is, of course, the great orthogonality theorem. Okay. So now this is going to be what we will use. But let's start from the fact that if you are in a direct sum space, that is, if you are dealing with some representation of a particular group which is reducible, then of course the space on which this representation acts is a direct sum of individual vector spaces, on each of which, of course, the irreducible representations act, right? So a basic vector there can be written down, any vector in your space can be written down like this. If each of these irreps have basis vectors v alpha 1, v alpha 2, v alpha 3 up to v alpha d alpha, so this set v alpha 1, v alpha 2 all the way up to v alpha d alpha, this set is a basis for v alpha, the one which carries the alpha at irrep. Now, in your direct sum space, you will have vectors which are from v alpha k, you will have vectors which are from this capital V alpha, you will have vectors from other spaces, you will also have the linear combinations. So a general vector would be something like this, something which you can always write in this form, where the sum, of course, runs over all k from 1 to d alpha. But this alone would have just given you a vector in the capital V alpha space. What you are really going to do next is you're going to sum up over all possible alpha.
So what space is capital V alpha to understand?
A capital V alpha is this vector space which carries which is it's essentially the subspace of the whole space, which carries the representation, the alpha at irrep. Remember, in your reducible representation, there are invariant subspaces. Each invariant subspaces carry the irreps. So V alpha is the alpha-th invariant subspace, which has a
Okay.
basis of its own. And the basis of the full space is made up essentially by taking all these basis vectors.
Huh.
So that's all you're really saying here, is that we can write down any vector by taking the basis vectors of the irreps individually and linearly combining all of them. Of course, because you are combining vectors from capital V alpha and also from capital V beta or from other capital V alpha, gamma, or whatever, uh, the resulting vector is no longer in any one of these subspaces. The resulting vector is a vector in the full space. So this is just a general statement that in a direct sum space, the basis vectors, if you take all the basis vectors for the individual subspaces which make up the full space, collectively, they form a set of basis vectors for the whole space. You can expand everything out in terms of them. Okay. So the game here really is now that we have this, how can we pick out from a vector in the full space just a vector which belongs to one of the invariant subspaces? Okay. You get my point? That is, instead of looking at this whole vector, there's an arbitrary vector in the whole space, it can always be written down like this. But maybe we want to pick out from here vectors or pieces of this vector which belongs only to one of the subspaces. Now, why do we want to do that? Well, one thing could be essentially this, that we want to know what are the bases, what are these subspaces. Suppose you have a reducible representation. So far, what have we done? We have figured out criteria which will tell us using characters whether a space, whether a representation is reducible or not, right? And if it is reducible, using the character table, we can find out how many times each irrep occurs in this. Okay, but what we haven't done so far is we haven't figured out what exactly is the reduction. We have, when I said reduction, when I have said reduction of a reducible representation so far, all we have done is count how many times a given irrep occurs. But how would you say really block diagonalize the full representation so that you will have individual block diagonal pieces? Because that will be important if you want to ask what, say, in the context of molecular vibrations, what we have been talking about or indicating about over the last few days. Uh, we have been counting how many kinds of vibrational irreps will be there, how many will be degenerate, and so on. At least we have just indicated how to do that. But if we ask, for example, what does this particular vibrational mode corresponding to this irrep really looks like? How are the atoms really moving in that mode? Then we will need to know what kind of vector actually spans that particular invariant subspace. Okay. So this is the kind of thing that we are going to try to figure out now. And maybe this will be clearer once we give a particular example. But let me just find out the theory first. And for the theory, what you need to do is first realize that if you take this vector and apply on it the operator representation of group element V, of course, what that is going to do is that's going to simply ignore this sum over classes or sum over irreps actually. Remember, the number of irreps is exactly equal to the number of classes. So this curly NC, which I tried to write here, is the number of classes or the number of irreps. And it's going to move over the sum. C alpha K are just coefficients. It's going to go and act on Vk alpha. And we know what will happen. It acts on Vk alpha, we are going to get V alpha L, D alpha Lk. This, of course, is nothing but the action of Lg on V alpha K, right? And remember, D alpha Lkg are just the matrix elements of corresponding to Lg, which we figured out using the basis V alpha 1, V alpha 2, V alpha 3, V alpha, D alpha. Okay? So this is the result. What you get ultimately is this. You have sum over K and L Now, among all the things that are here, there's only one thing which depends on the group element, which of course is the d alpha lkg. Everything else comes from the original vector. C alpha k is just a coefficient of the original vector. V alpha L are some of the basis vectors, right? This is the only term which really depends on the particular group element you're looking at. Now, what we are going to do next is we're going to multiply this by, or maybe what I'm going to do is, before I do that, let's rather irritatingly change notations a bit. I'm not going to call this alpha. I'm just going to call this beta. I can always do that, right? Because this also has to be beta then. All I've done is I've just relabeled the alpha to beta because I want to use this beta is of course a dummy variable of summation, and I want to use a particular value of this index for alpha, which I'm going to put in here. Let's say I multiply this whole thing by the matrix element. This is just a number, right? So it's just plain multiplication. Of course, if you do that, what's going to happen is that this side is going to become beta equal to 1 to curly NC, KL equals 1 to d beta, right? So this is just a multiplication by a single number, and you can move that number wherever you want inside the sum. Doesn't matter because this number, of course, does not depend on any of the sum indices. Fine. So what is the next obvious step to do? If you have an expression like this, what would you do? What is the obvious thing that you would do next? Of course, yeah.
GOT.
Yeah, well, you will try to go in for GOT. In fact, that's exactly what we did. Why we put in this Dij alpha G inverse in the first place, right? Of course, to get the GOT to work, you actually not only need this G alpha Ij G inverse, you also need to sum over all the group elements. And remember, this is the only term which depends on the group element. So this is what you are really summing up over. So what happens? If you do this, you get beta equals 1, 2. V beta L, and what the GOT gives you in the middle is mod G by d alpha, or d beta doesn't matter because there's a delta alpha beta anyway. Now we have to be a bit careful. Delta L J, the two extreme ones, delta Ki, right? I hope I've got this right. Remember, in the GOT, what you have is delta I prime, delta J prime. So the two extreme ones are the two closer ones. So here delta Lj, delta Ki. Now, of course, now that we have lots of deltas, it's easy to actually do the sum over, well, sum over beta, sum over K, sum over L. All these sums go away, right? So what you are going to get is C alpha. Everywhere you have a K that's going to be replaced by I, C alpha I, and V beta, so that's V alpha, and L becomes G. So, end of the day, what has happened is we have got this. You apply this operator. Remember, LG, of course, is an operator corresponding to a particular group element. You're weighting that operator by coefficients which come from the representation, from the irrep. And then you're just summing up all of them. So this resulting thing is of course an operator acting on V, a general vector in your vector space. The result is of course a vector right? So start with any arbitrary vector on your space, hit it with this operator, you're going to end up with a vector which is definitely in the alpha space, right? So basically, if you want to find out vectors which are confined to particular subspaces, and why would you want to do that? If you really started with your subspaces and built up your entire representation by forming a direct sum, you would of course have no need for such operators because you would already know what vectors go into making up your entire space. But here, what would usually happen in a physical problem is that the vector space comes given to you. It turns out to be reducible, but you now have to ask, okay, fine, how many times each array is there? That's a question we can answer just using characters. But if you want to ask what exactly are the forms which these vectors take, then you have to apply this projection operator. Okay? Is that okay? So finally, what we end up with is this definition for projection operator, Pij alpha, which by definition is sum over G belonging to capital G, sum over the entire LG. And by the way, since we are going to usually exploit the fact that finite groups at least always have an unitary representation, and every representation is ultimately equivalent to a unitary representation, all you have to do is change your basis. We will assume that the change of basis has been done, so we will usually use it in this form. We're going to assume that these matrices Dij's are unitary. So what we will get is D alpha Ji conjugate. Is this okay with everybody?
So every operator L has a different projection operator, or
No.
then
it's not the operators which the LGs are, of course, what they essentially tell you what the group action is, right? The group elements act on your vector space.
Oh, okay.
That's why we are interested in this. So the LG essentially tells you how the group elements act. But you can combine the LGs together by using coefficients from the irrep matrices, and that will give you projection operators. Okay. Now, of course, the downside here is for this to work, you need to know the irrep matrices. Okay. Unlike whatever we have been doing so far, where all you needed were the characters, and even the characters you could find out just without looking at the explicit matrices at all. For this one, we will need the matrices. Without the matrices, we will not be able to go very far. Okay, if you really wanted to know which ones are the vectors which transform according to this particular irrep, which particular combination, for that you will need to know this. Is this okay?
Yes, sir.
Now, there are some simplifications possible, by the way. Notice there are way too many projection operators here because there's one projection operator for each value of I and j, right? So there are d alpha square projection operators for the subspace alpha. But you can actually simplify things a bit. Often this is good enough. These are called diagonal projection operators. After all, you must realize that there are, in a d alpha dimensional irrep, there are only d alpha independent vectors, right? You can't have more independent vectors than the dimensionality of that particular irrep. So P alpha ij, of course, projects or acts on your original vector and gives you a vector in that subspace. But there are d alpha square of them, And you don't need that many. If you apply each one of the d alpha square projection operators on the vectors, any arbitrary vector, you're going to end up with d alpha square results. These d alpha square results are bound to be linearly dependent, right? Because there are only d alpha of them. Unless, of course, d alpha is 1. For 1D reps, there's only one possibility. But if you are going to more than 1D reps, p alpha ij's give you many more vectors than can possibly be independent, right? So very often we don't really bother about all that much information. We just look at these operators, which is simply just look at the j equal to I term. I'm just writing the unitary representation version. For the non-unitary version, you will just use this with I equal to j. Is that okay? So this will give you how many? This will give you 1 for each value of I, which means it will give you 1 for, give you d alpha projection operators. And acting on a vector v should give you d alpha results. Now there's one catch there. Oh, by the way, which result will you get? You will get p alpha I acting on vector v, arbitrary vector v, will simply be this result with I equal to j. So you will get mod g, number of group elements by the dimensions of the representation, c alpha I. Okay. Now, this actually is closer to what you would usually call a projection operator, right? What is the projection operator supposed to do? The usual kind. Say you take a vector 3i plus 4j minus 5k, and you want to project that piece part which is only along the y-axis. This should give you 4j, right? Just forgetting about the rest. Forgetting about 3i and minus 5k will just give you 4j. So here, that's exactly what happens, right? Apart from the factor of mod g by d alpha, which is just a numerical factor in the front, if you leave, don't worry about that too much. All you're going to get is exactly that piece which is in the ith direction in the alpha-ith irrep. Remember, the original v was simply sum over all alpha, sum over all k, c alpha, or let's write I here. So this was your original vector, right? This diagonal projection operator just picks out that part, c alpha I, v alpha I part, leaves everything else out, right? This is okay.
Yes, sir.
And one more thing, especially for one-dimensional irreps, this becomes even better. Because for 1D irreps, d alpha I are nothing but the characters, right? There's only one number. 1D irrep means the matrix itself is the character. And so all you do is just use the character table here for 1D irreps. Even there's not much sense in using the I index there because there's only one. So for 1D irreps, it's even simpler. You just take the group action, the operator which tells you what the group element does, multiply it by the character for that group element, and add up over all group elements. You're done. Okay? And that resulting operator will project every vector onto that particular 1D subspace. Now, how is that useful? Let me just show you how that is useful by just thinking of one example. Say, suppose I were talking of molecular vibrations, but for a square. Okay, you have to pretend that this is a square, or maybe what I will do, because this does give me ways of drawing things. So this is much better looking square than that so far. Okay, so this is our square, or close enough. And the molecular vibration, of course, would mean that you would talk of atoms at each four of the four corners, and as we did before, what we can do is set up basis vectors like this, right? And we have maybe these vectors labeled like this. And I want to be able to project onto the irreps which we have here. We remember we did carry out find out the character table for this, and we had a. Okay, how many classes does this have?
5.
5. And so 5 irreps, 4 of which were one-dimensional and 1 two-dimensional. That would be figured out simply by the d square sum is called mod g result. And we also found out basically full character table, right? We had this as one class, AB, reflections right down the middle as another class, then we have CD as another class, diagonal reflections, G as actually the second class in this list, and A, B, C, D, E, and F. Okay, which letters have been missing? F and H. The 90-degree and 270-degree rotations, which formed another class, and we found out that, well, identity, of course, will have, there's an identity representation which has all 5 ones, and then there are 2s, and then AB and CD would take +1, -1 values. I don't remember the order I wrote them in, but anyway, -1, -1, -1, 1, -1. And if you use them, you can easily figure out what G is going to be and what F and H are going to be. I assume this will do. I hope I'm right. And this one takes a bit more work, but using the orthogonality theorem, you can immediately write down what this irrep is going to be like. Okay. So now, given this character table, well, the character table doesn't have enough information for the projection operators in general, but for 1D irreps, the character table is enough, right? Because the diagonal projection operator, which in the case of 1D irreps is the only projection operator you have, just uses the characters. So suppose I want to ask myself, which particular displacement of all the atoms transform according to the 1D irrep, which is the identity irrep, 1, 1, 1, 1, 1. So what does this really mean physically? It means that we want to talk about a particular kind of molecular displacement which does not change when you do identity, which is of course trivial. Nothing changes when you do identity, but does not change when you do G. That does not change when you do A, B, C, D, or F or H. So does not change under a 90-degree rotation, does not change under a 270-degree rotation, 180-degree rotation, all of them. Okay. Now, just from this characterization, it's actually pretty easy to figure out what is going to be. Okay. Can anybody guess which way should the molecules, should the atoms be displaced, so that the displaced configuration does not change under any of the group elements? Just hold on. Hello. ও আচ্ছা আচ্ছা মাসিমা বলুন। Okay, so is what I said making sense? And does anybody remember why we are interested in this? Why we want to figure out what molecular displacement does not change when we do all these transformations? Of course, we have not really. Yeah.
It would be invariant under that irrep.
Yeah,
Right?
it would be invariant. That's fine. But that could be a nice mathematical question to ask. Why are we interested in that as physicists?
I think that will be a normal mode.
Yeah, okay, right. We did not really
And
talk about that in great detail before. We have not explained that before properly. But once we talk about molecular vibrations in the next class properly, we have already indicated this, right? We have essentially said that all these reduction of the reducible representation gives me various irreps, and these irreps, in this case, essentially are the various modes of motion. And if you have say multiple modes of motion with the same in the same irrep, then they would essentially be degenerate and stuff like that. But these are going to be various kinds of normal modes that we are going to get. Now there will be 4 one-dimensional normal modes and 2 two-dimensional normal modes. Right? That's what we figured out, because ultimately this particular 8-dimensional representation that we are going to get from the vibrations of the square molecule, that's nothing but a regular representation for this particular group, and hence it has every irrep as many times as a dimensionality. So what we want to do is figure out exactly what these terms are going to do. So let's see. Now, that is the reason why we want to do this. These are going to give us the various normal modes. And the great thing is, once you know the normal modes, even if your 8x8 matrix is very complicated, finding out the eigenvalue will be trivial, right? You know, when you want to diagonalize a big matrix, what's the hard part? You have to set up the secular equation, find out the eigenvalue, and then put it back and find out the eigenvector, right? And here it would have been an eighth order polynomial equation which you'd have to solve to find out the eigenvalues, and then plug it back to find out the eigenvectors. But if somebody gives you a matrix and its eigenvector and asks you to find out the eigenvalue, what would you have to do? If you were just given a matrix, asked to find out the eigenvalues and eigenvectors, you would have to do exactly what I said a while ago. But suppose somebody gave you a matrix and an eigenvector and asked you to find out the eigenvalue. How would you do that?
You put in the eigenvectors.
Yeah, you just apply the matrix on the eigenvector, right? And the eigenvalue will pop out immediately.
Sir, I had a doubt about something that you taught a little while ago. Could you scroll up a little bit in the definition of L of G as Ci alpha V alpha summation over there?
No, not
Like at the almost at the beginning.
yeah, this was a vector V, right?
Yes, sir. So when we up,
When you
okay,
apply
okay,
L
sorry.
of G, L of G is a linear operator, right?
Oh,
It's going
okay,
to
okay.
act on the vectors.
No,
So
I
it's going
got
to
confused with the definition. That's all. No, sir, not no. Doubt.
So it just
Yeah.
moves over and acts on V alpha K, and this is what V alpha K does. V alpha K does under LG. Okay, so can anybody guess what would the molecular vibration look like or mode look like under which transforms under this particular irrep? Remember, there are four one-dimensional irreps in this reducible representation, and two two-dimensional representations. Four of these, once each. So I need to figure out what these normal modes really look like. So can anybody guess?
Corresponding to the identity, it will be like the molecule expands and contracts.
Yeah, so that's right. So basically what it will look like is something like this. It will look like the molecule has to go like this. All the four Of course, that's just, so that means, well, we are talking about a specific vector V, which has equal component for E1, E2, minus E3, E4, minus E5, minus E6, E7, and minus E8. It's easy to see that this particular, suppose a particular molecule has been sort of displaced like this, all the atoms have been displaced like this. At 45, these are of course meant to be at 45-degree angles. My picture may not make that very clear. And this of course would mean the entire molecule has expanded. Let me also point out that this is just going to be in this vector space, which means multiples of this particular vector would mean it's just going to expand more or less, or even with negative multiples, it's going to go in the other direction. So basically, it's a breathing mode. Square just expands out and shrinks back. Okay, but you can easily check, right? If you did a 180 rotation, what will happen? This particular atom will move here, but this displacement in the 180 rotation will turn and move here, right? It will just become this one. Is that okay with everybody? Can you see, for example, that under A, which is a reflection like this, not only does the square stay the same, even the displaced square, after all these atoms are moved out, even that stays the same, right? Is that okay? Yes? No? Maybe? Or
Yes,
suppose I did a 90-degree rotation about this point, which is F. This point will move here, but this vector will also turn this way, right? Now, in this particular case, the identity one is actually pretty easy to figure out that this is what the displacement is going to be without using any group theory. You don't need all these character tables and operators and stuff like that, right? You can always just sort of figure out that a uniform expansion will not change under any of these symmetry operations, because after all, a square is still a square. So whatever is the symmetry of the original square stays the symmetry of the displaced square, and so on, right? However, figuring out the other normal modes, the ones which correspond to maybe this 1, 1, 1, minus 1, minus 1, it's not that easy. All of these can be done, especially for the 1D representations. You can actually figure this out without really taking much help from the projection operators, but it takes quite a bit of effort. So let's try to use the projection operator approach and try to understand what that's going to be. Okay. And for the projection operator approach, what I'm going to do is I'm going to just start with any arbitrary vector which comes to mind in your vector space. Maybe I will just start with this. I will start with, I need a color. Let's say black. I'll just start with a vector which points along E1. Okay. So this, by the way, is a vector in your original full 8-dimensional space, which just has one non-zero component, the one along E1. All the other 7 components are 0. Right? You get that? I'm just starting with this. I could have started with anything else. This is just a simple, easy starting point to start from. Okay? So then what I'm going to do is apply my projection operator, which for this particular representation is simply this, chi alpha LG, right? Which is chi alpha G's conjugate, but these are real characters anyway. And so, in this case, all the chi alphas are +1. So what we do, we have 8 group elements to apply, and we are going to apply each of the 8 group elements on this vector. Of course, we are not going to apply the group elements on the vector, but the representatives of the group elements LG, the operator representatives on that vector, and weight the resulting thing by character, which in this case is just 1, and add up. So what happens to this when you do identity? Of course, nothing happens. This vector stays this vector. What happens to this vector when you do A? Yeah, A, remember, is this reflection. then this vector goes here, right? First of all, the point of action of the vector changes from here to here, and it's in the same direction, like this, right? Is that okay?
Yes, sir.
Then comes question of doing B. B is this reflection along the vertical. Of course, that means the point goes here and ends up pointing the other way, right? So that's B. C is this reflection on this diagonal. That would mean this vector gets reflected along the diagonal, becomes this vector. What about D? Reflection here. So this vector goes to this point, this corner, and ends up looking like this. Is that okay? Everybody with me so far? So we have done E, A, B, C, D. We have to do F. F is a 90-degree rotation. If I do a 90-degree rotation from here, what happens? This point moves here, and the vector points upright. Okay? 180-degree rotation. This point ends up here. Vector looks like this. And the 270-degree rotation, the point moves all the way here, and the vector ends up looking like this. Okay, so now we have 8 black arrows in this picture, right? These 8 black arrows are the result of LG acting on each one of the vectors V. And now what we are supposed to do is weight each one of these by the character, which in this case is just 1, and add them all together. And that will give me the particular vector which is spanning the 1D irrep corresponding to the identity character. And it's easy to see that if you add all these 8 vectors together, what will you get? You'll get exactly the blue lines, or of course, larger versions of those blue lines as arrows, right? Is it okay? Everybody?
Yes, sir.
Okay, good. So that essentially tells you how, if you could not guess that the identity representation essentially has this kind of vibrations, where the atom is just moving out, or the molecule is just moving out and coming back in. Okay. Remember, it's also coming back in because this is just a vector space, right? The vector can also be negative, so can have a negative component, which means it will point inwards then. But then all the 4 will point inwards, and the whole atom will shrink. So this is a normal mode, which is a sort of obvious normal mode to think about if you have a symmetric molecule. The whole thing breathes. This is also called a breather mode for this obvious reason that it expands and contracts, the way a lungs is supposed to do. Okay, what about the other representations? Well, this one should not be too difficult. Say it has negative signs for C, D, F, and H. Okay, so let's see if I can cut the clutter here a bit. Maybe. So maybe. Okay, this is your original one. Identity, of course, keeps it this way. Then we have G, which gives you this one. That's fine. This is okay. This is okay. This is okay. A, B, A does this, B does this. These are also okay. C and D, you have to reverse the result. C, of course, was this one. This is what you are going to get. That was what LC did to the vector. You need minus LC, minus sign because of the character. So that's pointing down here. Well, D, that was what D did. What you need is this one. Okay. And F and H, 90 rotation, F would point this way, H would point up. So basically, now you look at the vectors, what they're doing. This is what the mode looks like. So can anybody tell me what will the atom or what will the molecule look like while it's vibrating this way?
Rectangular.
Yeah, it will essentially be a distortion mode. In the square becomes a rectangle, elongated rectangle, elongated along the x-axis as it's being drawn now. But you should realize that, of course, this vibration will go like this, right? Back and forth, which means you will end up with a rectangle at one part of the phase, and other phase it will look like this kind of a rectangle. So it's going to stretch along the x-axis, then it's going to squeeze along the x-axis, stretch along the y. Okay, so that's another possible normal mode. This one would not have been that easy to figure out without help of this projection operator thingy. Look at that. The previous one, the identity one, given enough time, anybody could have guessed. But this one takes a bit more effort. Let me try getting rid of all these extra lines that I've drawn now. Oops. I think I'm keeping on hitting the undo and the redo buttons in succession.
Sir, so if you choose some other general vector instead of
Yeah, that's
E1,
a good question. What happens if I choose something else? The answer is, as long as I'm choosing, as long as I'm lucky in my choice, I'm going to end up with a vector in that irrep space. Why do I have to? Okay, what would constitute being unlucky? Can anybody tell me that? Remember, as long as you're dealing with 1D irreps, there's only one basis vector, so I don't really care. No matter what vector I start with, I should end up getting that. Can anybody tell me what would be unlucky? When will I fail in doing this? As has been rightly asked, I started with a specific vector, right? I started with a vector along E1. What happens if I started along something else? You can, of course, play and try, right? You can start with a vector along E2, or maybe some vector, maybe even you could start with this. Why not start with, well, why don't you start with this? Remember, the vector that you start with talks about displacement of the molecule as a whole. Does not have to be one atom just displaced. That was just for convenience. I could have started with this configuration, right? Is that okay? Everybody with me? That this is a admissible vector in the vector space we are talking about. Remember, our vector space is 8-dimensional, and that talks of displacement of all the molecules. Suppose I just started with this, all these molecules displaced by 45 degrees like this, and then tried to apply the projection operator for, let's say, the identity representation on this. What will happen? Let's try checking that out. Let's get rid of the black lines, or at least imagine that the black lines are not there. Maybe I will try erasing the black lines. Yeah, so our cyan lines, the blue ones, this is our initial V on which I'm applying the projection operator. Let's just say we are going to try to apply the projection operator corresponding to the identity representation of that. Okay, there are 8 things to apply. First, the identity, which of course does nothing. Then comes G. Let's go in order in which the table is written. Next comes G. G would be in a 180 degree rotation. So of course this point will go here. But can anybody tell me which way will the vector point after a 180 degree rotation? Took this vector, so where will this point go for example, after a 180 degree rotation? The tip of this vector.
1 by root 2 E6 minus E5.
Yeah, I don't know the number. Will it look like this vector or a different vector?
That vector. That vector.
Yes, it will look exactly like this vector, right?
So it will basically be the rectangular oscillation that we saw.
Are you sure? We have just done G.
Because if we do the reflections and if we do the reflections by the diagonal, then it changes. Like then,
Yeah, if you do A and B, these stay the same. So A and B also repeat these. So you'll have four. So for E, G, A, and B, you will have four vectors, each pointing along the same direction, right? Is it okay? For all of E, G, A, and B, that will happen. What happens with C? If you reflect it like this, you'll end up with a vector pointing the other way for all of the four. Sorry. For C, of course, this vector does not come from this one. This vector actually comes from this one. This blue one reflected here becomes this one. Is that okay? What happens with D, which is this reflection? Then this vector becomes this one. This vector becomes this one. This point moves here, but this arrow becomes this arrow. And this point moves here, this cyan arrow becomes this red arrow. You should be able to figure out that F and G also gives you four vectors like this. Basically, you have four vectors pointing in the original direction coming from the action of E, G, A, and B, and four vectors pointing in the opposite direction because of the action of C, D, F, and H. So what is the sum of all these?
0.
0. So, and why is it 0? Simply because you started with an irrep, with a vector which is already in one irrep, right? You started with a vector which is in the second irrep, which forms the basis vectors for this irrep, right? We figured that out a while ago. That you start with a, we tried figuring out what the irrep corresponding to this will look like, and we found that it will look like this kind of rectangular distortion mode. Okay. I'm pretty sure that molecular vibration experts have special names for these modes. I don't really know them, so I don't care. It looks like a distorted rectangle to me. But if you started with a vector in that mode and applied the projection operator for the identity representation, you're essentially asking how much of the identity representation is there in this particular representation. The answer is none. So you're ending up with 0. Okay. So what has happened? Well, nothing wrong has happened, but if your aim was to find out a vector which spans the identity representation, then you are out of luck. Then this particular choice would have given you nothing. We have just told you that the vector part of this particular starting configuration that points in the direction of the identity representation spanning vector is 0. Which of course tells you nothing about which way the identity representation spanning vector points. You get my point? You start with an arbitrary vector, I don't care which one. You are just going to get the piece which points towards that particular basis vector which spans the identity representation. We just happen to start with a vector which has no piece in that direction, you're going to get 0. And then your procedure, if the aim of your procedure was to find out a vector in that direction, that fails. Okay, but you should realize why did that happen here? It happened because we very specifically chose for our starting configuration a vector which I knew was not in that irrep. I knew it was in another irrep, right? Now realize that unless you're very, very unlucky, if you make an arbitrary choice, it's very unlikely that that vector that you have started out with will not have any piece of the irrep you're looking for. Is that okay? Anyway, so happens that is the case, then start again with another vector. As simple as that. Is this okay with everybody?
Yes, sir.
And now there's also a bit more of to it than that. For example, there are there are one-dimensional representations that they only occur once, right? Each of them in this particular reducible representation. So here, unless I'm very unlucky and I get a 0 when I apply my projection operator on the vector I start on, I'm going to get whatever, and whatever vector points in the right direction, and that's it. Then my work is done. Okay. However, there are two-dimensional representations, right? And of course, why are there two different representations despite being both the same irrep? Because their basis vectors are different, right? You have 8 independent basis vectors ultimately. So 4 of them, of course, span the 4 one-dimension. So once we look at the basis vectors, we span the irreps. 4 of them span the one-dimensional representations, but the other 4 span the same two-dimensional representations. So there are 2 independent vectors each for each of these two-dimensional representations. And so there, of course, if you start with a given V and apply the P, the PII in that case, you are only going to get 2 vectors, right? You will not get all 4. So you will have to start with different V's and apply them. Or you may have to start with the non-diagonal original projection operators and apply them. When that may work, it might just so happen that in one run you may not be able to get all of them. You may have to start with a different starting vector to get all of them. That's always possible. But ultimately there's only a finite number, and once you have 8 of them, you're done. Is that okay? And as I was pointing out, the chances of a vanishing result is very, very small unless you start deliberately with a representation, with a vector which is already in some other irrep. You are not going to get 0. Okay, and but the problem might be that, especially for multi-dimensional irreps which occur multiple times, you may have to work a bit harder before you get all the basis vectors. Is my point clear? Yes, no, what?
Maybe, sir.
Maybe. Okay. That's not very encouraging, but let's see. No, at least do you agree that it will be very unlikely to get a 0 after you apply the P?
Yes, sir. I got it. I'll just need to think a bit more.
Okay. Fine. Now,
Sir,
yeah, go ahead.
I had a doubt. You said ki if we even if we get 0, like it's more likely the case that it say for this case where we considered the rectangular vibration and it corresponded to the second irrep, right? And then you said ki we can't say the contribution of the identity irrep in that. Can't we like say that there's no contribution from that directly?
Yeah, we can say that. But if your aim is to find out how much of the identity irrep is there in this particular starting configuration, which is an important piece of information for some applications, of course, then the answer 0 is quite a good enough answer, right?
Yeah.
Having no contribution is also important to know about that there is no such thing. However, if your aim, as is our aim right now, is to find out which vectors span the various irreps, so that we can talk about what are the normal modes of vibration. What kind of vibrations do they occur? Remember, we have already done 2 of them. We have found out that the normal modes of vibration of the molecule are essentially, one of them is breathing in and out, the other is changing into a rectangle and changing back. Okay, not too bad, right? With very minimal information. Remember, we are not even talking about what the exact forces are on the molecules right now. We have not said anything about that kind. We have not talked about what kind of force matrix acts on the 8 molecular displacements. But we have just said that this is there is a symmetric molecule, so the force matrix has to obey those symmetries. And from that and that alone, we have been able to figure out that a breathing mode and a rectangular distortion mode are going to be normal vibrations. That, I would say, is quite a huge achievement. Wouldn't you?
Yeah.
And then, of course, if you knew the force matrix, then of course, suppose you have this 8 by 8 matrix you need to diagonalize. Fine. You could have diagonalized it by brute force. But here, if you know the eigenvectors already, all you need to do is just plug it in, you are going to get the eigenvalue. So the amount of work you need to do gets reduced drastically. More importantly, it gives you an insight as to why these are the particular modes you have. And if you destroy some of these symmetries, which modes go away? Okay, let me just do one more. 1, 1, minus 1, 1, minus 1. Let's look at this one. So quickly, let's use the draw arrow thing. Again, let's start with this vector. This has worked well enough for us so far. And just notice this one thing, that if you displace just one atom and not the rest, the chance of that being in one particular irrep or not having any other irrep is rather small. So, okay, but if it so happens that you get a 0 at the end of the day, you have to start with some other vector. That's it. Okay, but let's look at this one now. Identity, do this. Reflection to 180 degree, this one. AB, A, B, this. Okay, I'm looking at this one, right? So, sorry, I made a mistake. A would have to be this, right? And B would have to be this. Can you see why? Of course, A and B produces this vector and this vector, but you have to weight them with a minus sign. And that's the game. Sorry. C, D, plus sign, F 90 degree rotation, this one, 270 rotation, so again I messed up the sign of the arrow. I forgot that this only works in one direction. Okay, so these are the 8 LGs weighted by the chi's acting on the original vector. So what does the displacement look like? It looks like so what is this mode like? What will the square look like when it vibrates like this?
I think it's called a rhombus.
Yeah, so it will essentially end up looking something like this. Maybe I'll take this color. So square essentially bends into a rhombus, stretches in one direction, squeezes, so it stretches along one diagonal. Remember, in the rectangular case, it was stretching along one side and squeezing along the other. Here is stretching along one diagonal, squeezing along the other. But that of course is only for half of the cycle. For the other half of the cycle, it will end up looking like this. It will. It will end up looking like this rhombus. So it's going to, this atom is going to move out, and then move in again. And when this atom moves, these two atoms move out, the other two atoms move in, and conversely. So I think you should be able to imagine what the motion will look like pretty well. So this is ultimately not that difficult a thing to think about ultimately, right? Because Because of the symmetry of this thing, the ultimate motion is sort of going to be simple. Of course, what complicates matters is that these normal modes happen only when you set up specific initial conditions. Otherwise, what would happen is you will see a complicated combination of all these normal modes together, which will look very horribly complicated. Okay, while we are at it, why not look at this one? Okay, once again, the last one now. 1, 1 minus 1. This is the 1. 180 rotation. That's exactly that. A comes with a minus sign, and so does B. A, B. Okay, CD also comes with minus sign. So C and D, which would have been this, ends up being this. Okay, F and H. Those are the only things left. F, a 90 rotation would have made it look upright, but in this case looks okay. 90 rotation. Okay, I'm looking at the last line, F and H. Okay, so F and H are positive. So this, oops, again forgot. Okay, I'm not even going to add up the vectors and write down what it looks like. Can anybody tell me what is this motion?
Rotation.
Yeah, that's exactly right now counter clockwise rotation, right? So as I said, among the irreps that you find out, there will be non-vibrational modes. 2 translations, 1 rotation. This is the rotation mode. Okay, and we know that this corresponds to no restoring force, so no frequency. Okay, so what I will do is I will leave you to play with the 2-dimensional irreps. By the way, that takes a bit more work, not very much, but does anybody remember what the 2D representation looked like?
2 minus 2 0 0 0.
No, that was the character, but the character is not enough now. That's the point. You need to know the representation matrices. For 1D, for the projection operator game, characters have too little information. By the way, you can even use the characters in a way. What you could do is just take this projection operator, the diagonal one, and then sum up over all I. If you do that, you're going to get just Ci alpha, Vi alpha piece towards that direction. So that's also a vector in that space. So even with the characters, we may be able to make a bit of an headway, but not all that much. So if you tried that, it was 2 minus 2 and all zeros, right?
Yes, sir.
This should be, that's trivial, right? Because orthogonality will immediately tell you that. So just try it with the characters. The result will be simple. You are just going to do E and G and weight them with 2 and minus 2, or 1 and minus 1, doesn't matter. So you will know that one basis vector will be like this. So maybe I will just get rid of all these extra green lines. Okay, but that's too little information. That's, you start with this, you get this and this. Okay, you start with some other vector. Maybe this. Oh, oops. But the point is, you can start with many other vectors and see what happens, and you can actually ultimately end up spanning the whole space.
So the rotation has -2. So shouldn't that second black arrow be in the opposite direction?
Wait a minute. Which one are you talking about?
For the two-dimensional representation, the G has -2, right?
Yeah. Right. I made a mistake here. You're right. Yeah, this is this would have ended up giving you pointing this way, but -2 ends up making it point this way. Now, you should realize that this essentially is telling you that these two atoms moving and these two atoms moving, they don't really give you a normal mode, by the way. They just give you basis vectors which spans your normal mode. But they give you too little information here because you need 4 basis vectors. Not too easy to find all of them this way. But all you need, it's not very difficult. All you need are the D's. The 2D, sorry. I'm forgetting. You just need the 2-dimensional irreps. These matrices. In fact, you don't even need all of them. You just need the diagonal elements. Okay? And also, just to remind you, that's not too difficult to figure out. This was the 2D irrep that we found out a 2D representation of this group just by applying the group elements on these two simple basis vectors, E1 and E2. Okay, not this E1, this E2, but E1, E2 centered around the square, at the center of the square. And we just found out what the matrix representation was. And we are not even interested in the full one. We just want the diagonal elements, right? So, straightforward, D2E. E2E is, of course, 1, 0, 0, 1. What is E2A? Under A, what will happen? A is this reflection, right? E1 will stay E1. E2 will change sign. E2B. E1 will become minus E1. E2 will stay E2. E2C. E1 changes to this reflection. E1 changes to E2, right?
Yes, sir.
Even in the position operators, this will not come at all. E2D. D is this reflection. E1, E2 will change to minus E2, E1. So all these matrices are pretty easy to write down. And just the diagonal elements, that's all. D2, F, 90-degree rotation. E1 becomes E2, right? So 0, 1. E2 becomes minus E1. D2G. Again, I really don't need all of this. I can figure out what the signs are, but the diagonal elements are going to be 0. That's all I really need. So through centric rotation, E1 becomes minus E2. The E2 becomes, wait a minute, E2 becomes, after 92 centric rotation, E2 becomes E1. Yeah. So these are the 8 matrices, right? And how do we know that they form an irrep, by the way? This is a representation. I can find this out by just applying the group elements on the basis vectors of your vector space, which carries on which the group elements act. Fine. How do you know that this is an irreducible representation? Yeah, go ahead. How do we know that?
Summation NC of characters of a class should give the size of the group.
LC characters of the class should give a size of group.
Summation over all the classes of the characters. I mean, something.
Yeah, that's NC chi-C mod square, not NC chi-C. It's chi vector dot chi vector.
Yes, sir.
Yeah. That's one very good answer. If I knew nothing else about this this group, I could have just figured out that the characters are 2, 0, 0, 0, 0, and -2 for the G. And if you just took 4 square plus 2 square plus 2 plus -2 whole square, weight them by 1, because in each case the class has only one element. And with 8, which is the number of elements in the group, so I'm done. So this is, and that's the criteria written for irreducibility. That was one way of looking at it. The other way is even simpler. Right now, because we already know the character. If I knew nothing about the group, about representations before, that would be the way to do this. But since we already know the character table, and we know that there is an irrep with 2 -2 0 0 0 characters, and this is a representation with 2 -2 0 0 0 characters. This has to be the irrep, right? You can easily see that the characters are 2 for this, -2 for this, and 0 for all the rest. Okay. So now with this information, let's proceed. Let's try finding out there will be 2 projection operators for this 2-dimensional representation. Let's say P2, 1, 1. This is diagonal projection operators that I'm going to talk about, P2, 1, 1 and P2, 2, 2. So what is P2, 1, 1? Okay, that's 1, 1 means you just look at the 1, 1 element. That's it. You weight your LGs with the 1, 1 element. So it's really very simple. Nothing much to worry about. Okay, let's draw our original rectangle again here, or original square. And now I'm just going to start again with maybe just this arrow. So that's D2E. D2E 1, 1 times LE acting on the vector. But then you need to do D2A 1, 1 times LA. LA, of course, gives you this vector, and D2A 1, 1 times LA also gives you this vector. What about B? B would have given you this vector, but you have to weight it with the -1, so you are going to get this vector. What about C? C gives you nothing. No contribution, no contribution, no contribution, no contribution. The only contribution comes from D2G. D2G would have given you this vector, but gives you this vector. Okay? So if you start with the vector pointing this way and apply P2, 1, 1, you get this mode as one possible vector spanning your 2-dimensional irrep. One of the spanning vectors. Which one should this be? What is this motion?
Translation.
Of course, this is just a translation along the x-axis.
So the other one would be sort of trapezoidal.
No, wait a minute. The other basis vector for this particular irrep, what should that be? You should get that very easily, right? All you have to do is just apply one of the group operations on this. Remember, you have an invariance. Is this vector invariant under the group operations? If you think about all the previous cases, all the four examples we have worked with so far, ultimately, when you have a configuration, let's say, let me just temporarily draw on this picture, the rotation mode. This was the rotation mode, ultimately. What happened to the rotation mode when you applied the 4 group operations, the 8 group operations? Just think of these blue arrows. What would happen to them? When you do identity, of course, nothing happens. Fine. When you do A, this reflection, what happens? Do you get this set of blue arrows back? Come on, if you reflect along this line, what happens? This arrow
Yes,
goes
but in the opposite direction.
you get it in the opposite direction. Ends up
So
looking
it's
like
in
this.
any.
And that's also not a surprise because the A gives a minus sign here. Right? If you have 180 rotation, you get the same, exactly the same thing. Under the reflections A, B, C, and D, it changes sign. And another rotation doesn't change sign. Right? By the way, that's also so easy to understand. Rotation with this notion that rotations ultimately are related to angular momentum, which is a pseudo vector, and pseudo vectors behave differently under rotations and reflections. I will just let you ponder about that. It's a pseudo vector nature of angular momentum, which is really at display here. But the point is, ultimately, you get essentially get the same vector with a sign change at most, right? And why is that? Because basically you have a one-dimensional representation which is spanned by just this original configuration of blue vectors. So whatever you do, any of the group operations you apply on that, because you have hit a one-dimensional array, you are going to get a multiple of whatever vector you started with, right? But now that you are dealing with a two-dimensional array, you apply group operations, it's no longer guaranteed that you're going to get the same vector back, right? You're going to get something else in the two-dimensional representation. So easiest way of finding out the other vector was just to check what happens to this vector. By the way, this is not 4 vectors. This is one vector in our 8-dimensional space. This one vector, what happens to that under the group operations? Under identity, of course, it doesn't change. Under A, it does not change. Under B, what happens to it under B?
Vertical translation.
Under B, remember is B, by the way, is this one, this reflection.
Or translation in the opposite direction.
It again gives you translation again in the x direction. So it doesn't give you a new vector, right? It's just a change of sign. But under C, which is this reflection, it gives you a bunch of new vectors which point. By the way, under C, this arrow doesn't come from this one. It comes from this one. But ultimately, you end up. So it's easy to see that this will be your other basis vector for the 2D array, right? Can you say why it has to be the other basis vector? Simply because it's a two-dimensional invariance of space, right? So if you start with a vector in that space, apply your group operations, you have to get a vector in that space. And if you get a vector which is independent from the first one, you now have 2 independent vectors in a two-dimensional space. So you're done. You have found your basis, right? Of course, you could have found the same vector, by starting with a vertical vector initially, not a horizontal one, and applying the same trick and see what happens. By the way, let's see what happens if I started with if instead of doing this, instead of starting with this final basis vector that we have, the 4 black arrows, and then applying the group operations, what happens if I did this? Let's start with this one and apply D2E, of course, as that one. D2A, A is this reflection, D2A will be this one. And then D2B, reflect here, go this way. And what about D2? Well, here the job is rather low, right? You don't have to do a lot. D2G, 180 rotation. Oops. Again, but this time with a minus sign. So this is the other representation's basis vector, by the way. You're using the top one element in both cases, starting with two different vectors. You've essentially ended up with the other normal mode, in which the square essentially changes like this. Yeah, this was the trapezium we were talking about. One side expands, the other side contracts. Then that of course is temporary, transient. That will happen. A while later, what will happen is this side will contract, that side will expand. Okay. So that's one normal mode. What's its corresponding partner in the same erupt? This, of course, is not the partner to the translation. The translation is not is of course an erupt, is part of an erupt, and its partner, of course, is the y direction translation. This one is different. This one is the other erupt. What would its partner be?
You get the partner if you act C or
yeah, you
D
could get the partner that way, but you don't have to. Can you just guess?
Yes, a trapezoid
in this particular version,
direction.
Yeah, it's just a rotated trapezoid, right? Isn't that the case? Because all you have to do is, after all, we started with a vertical vector. Why don't we start with the horizontal vector? And okay, how will I get that by our prescription of the projection operator? Notice we started with two different starting points. One was this vector. Sorry. And applied DG11 on all of them times LG and added up. I got the translation along the x-axis. I started with the vertical vector, did D211 G LG on all of them, ended up with this mode. If I wanted to get the other two modes directly, not by starting with this mode and then applying the group operations or so on, or guessing, what would I do? Well, remember, we have only applied P211 so far, right? We have not applied P222. Why not give it a try? That is, use the other diagonal element, that is this one. Okay, this one, of course, let's just give it a quick try. This will do nothing. Let's start with the blue one. What happens to the blue one? D2E gives you this, D2A gives you this, right? D2B gives you this, and the only other non-zero element is D2G, which would have given you this but gives you this because of the minus sign. So you can see what have you got? You've got the other trapezoidal mode, right? Are you following me, or have I completely lost you by now?
No, sir, it's okay.
And what about how do I get the vertical translations? Simple. Start with a black arrow. Start with the vertical one, and apply P222. 22 would mean, again, this one is E. A with a minus sign. A is this reflection, would have pointed this way, ends up pointing. Oops. Again, keep on forgetting simple stuff. Oh. Right, this is what it would be. And you just apply B, B, of course, has a plus 1 here, so B will give you this. And if you apply G, would have given you the vertically downwards arrow, but because of minus sign gives you this. So ultimately, if I get rid of the other lines on the board, which unfortunately got rid of my rectangle as well. But anyway, these 4 lines, you can imagine the 4 corners of the square sitting there. That gives you the other translation. So we have managed to find out all the 8 basis vectors with rather minimal effort. Should realize that diagonalizing an 8 by 8 matrix is a much more daunting task than this. And now that you have all the eigenvectors, you can just apply the matrix on them, and you've got your eigenvalues as well. Okay. So the projection operator essentially helps you to pick out basis vectors in a given direction and in a given irrep. Very little work for 1D irreps. For more than 1D irreps, slight bit more work. Especially if, and also even with 1D irreps, it would require more work if multiple copies of that particular 1D irrep were occurring in your representation. Doesn't happen in a regular representation, of course, but it can happen in other representations. So the same irrep may occur 3 times or 4 times. Then you may have to start with 3 or 4 different starting vectors. Independent starting vectors, of course, and apply the position operator and get the results from there. But this is essentially how you find the basis vectors. Is this okay with everybody? Yes? No?
Yes, sir.
Okay, so anybody has any questions now? Or if not, we can call it a day today. I thought I will take a short class today, but ended up taking a rather long one. But I hope it's sort of clear, and we are going to use this for the next class on. So ask the other two to also watch the video. I will try to upload the video as soon as I can. Any other questions? If not, let's call it a day today. So I will see you on Thursday.